case is stoic with acids and bases. So I kind of have some demo-ish kind of stuff. None of it's super exciting, but I have some demo-ish stuff over here. Talk about what the definitions of an acid and base is. A little bit more sophisticated definition than the middle school definition. We'll kind of go through the discussion of what actually does it mean to be a strong acid or a weak acid. And then there's kind of a funky skill that comes up in here in identifying parts of an acid-base reaction. And then we already kind of done this a bit, the neutralization reactions. Just a special case of stoic, so don't freak out about this part. It's kind of why I put it on here last. Once you realize that this is literally just stoichiometry, it's not a huge deal. The one thing that I did not do on this warm-up question back here was to have us write like the ionic, net ionic, complete ionic equations, or it's only two, the complete ionic and net ionic equations. So make sure that you're really comfortable with that particular skill. A lot of the homework is associated with that. And a bunch of the test questions are associated with writing those ionic equation forms. So make sure that you're comfortable with that part. But like I said, I didn't go through that today. We'll do some ionic equations today, but not with a precipitation reaction. Okay, so just so you know what the kind of arc of today's storyline is, yeah? We good to go? So acids and bases. You guys know what acids are? I'll talk about these two guys' names. So there's a dude. I'll put his name up here. He was one of the first guys. He was an early researcher. His name is Arrhenius, is how you pronounce that. It doesn't look like it, I know, but that's how you pronounce that. It's kind of like a silent H. This is the guy that came up with the definition of acids and bases like you know it. And his definition works about 80% of the time. Doesn't work when you get to some higher level chemistry, which is why later scientists had to kind of adapt his definition. But his basic definition of what an acid and a base is actually pretty darn straightforward. So we don't have to worry about it a whole bunch in terms of what it is. Acids. This is the definition I used the other day. How do I know if it's an acid? Hydrogen where? Yeah, first element. It has a hydrogen cation and it has some other anion. Can be polyatomic, can be binary, can be all kinds of stuff. So the typical acid definition is like the one that you know. So you've got something like, you know, H2SO4, you got HCl, HF. The friendly one. No, the friendly one. Hi. Hydroiodic acid. Yeah. So it can be any of these. Anything that's an ionic compound that's got hydrogen at the first, that means it's an acid. And that's a pretty typical thing. What do you guys know about the pH of these things? Something in that range. pH is less than 7. We'll talk a little bit about what pH means today and where that comes from. But a pH less than 7. And then there's a variety of different acids that are out there. There are some things that contain hydrogen that are not acids. That one is got a hydrogen in it, but this in and of itself is an ion, not technically an acid. That is technically, oops, sorry, 1 minus. An ion with a hydrogen in it, it's not technically an acid. Oh man, if I could write C6H12O6. Lots of hydrogen in it. Not an acid. This is a molecular compound, so it has to be an ionic compound. And that's the big difference with these. What makes it have this pH, this. What makes them acids is that when these things dissolve in water, and again, they're aqueous solutions, when they dissolve in water, they release hydrogen ions. Not only do they have hydrogen in them, but they release them. Hydrogen's ions are chemically very reactive and like to go attack other things and do chemistry. They're like freshmen. They're just super enthusiastic about doing stuff. And so you let them out into a container and they'll start eating metal and reacting with all kinds of stuff just because very much like freshmen, exactly. So, but anyway, you put these things in water, they're considered acids. They're not necessarily always acids. Just as a quick aside, this particular thing, sulfide gas, usually it's in this form and it would not be considered an acid. If you bubble it through water, That's called hydrosulfuric acid. So it depends on where it is. When it's in gas form, it doesn't have those hydrogens released, so it's acting like a gas. It's acting like almost like a molecule. When we put it through water, it can start to release some of those hydrogens, and it can weakly act like a gas and do some other things. So again, it's about whether or not just does it have hydrogens, but are those hydrogens available to do the nasty stuff that they do. On the other hand, what's a base? Hydroxides, yeah, it's the opposite side of that. And this is the Arrhenius definition. And these are things that have hydroxides in them or hydroxides available in solution. What kind of pHs do they have? Yeah, pH greater than 7. And again, it just depends on how close to 7 you get. The further away from 7, the stronger it is. So Arrhenius, pretty simple definition, acid base. It was either hydrogens or hydroxides. And he came up with that simple idea of a neutralization reaction, that when you take an acid and a base and you mix them together, you get a real, I would say, a basic reaction, but that sounds really stupid when we say that. When you have an acid and a base, I'll let you figure out why I wrote it that way. Acid and a base, you always get two products. Water's one of them. And again, I write it in its kind of ionic form just to point out where the pieces come from. And what's the other thing? That and that. It's actually Ba. You always write the positive first. But yeah, it's Ba. And that thing is called salt. If I throw it at you, it's a salt. Thank you. Thank you for groaning. Thank you. Bam. All right. So literally, that's it. When you do acid-base reactions according to the Arrhenius definition, they're pretty simple. Pretty simple. You have some sort of an acid which has a hydrogen ion, some sort of a base with a hydroxide ion. When you put them together, you get water and salt. What's the ionic equation for this? Complete ionic. Take that apart. What is it? We're assuming aqueous, whatever that is in aqueous. What kind of ions do we get here? B plus. Okay, what do we do with the water? Morning. Does the water separate into ions or does it stay together? Stays together. So this is HOH. Liquid is the physical state of that. It is not a precipitate, but kinda. And then B and A. Most likely, it is possible to have this be a precipitate as well. Depending on what the things are that you've got in here, you could precipitate that out, although it's pretty unlikely. So, an ionic compound formed between a metal and a nonmetal, otherwise known as the product of an acid-base neutralization reaction. Yeah. Some of the questions in your homework will ask you to kind of work backwards and say, all right, I have this salt. Give me the name of the acid and base that I could create that from. So you could have a salt, something along the lines of, you don't have to write this part down if you want to. Let's say you have the salt, what would work? Yeah, that's boring. What would be the acid and base? I'm going to do this one. What would be the acid and base that I would use to make that salt? Mg is the positive one, and OH. And then this would be the negative one, H2SO4. So you can work backwards to figure out what acid and base to be used to produce that salt. So don't let that freak you out. It's just a different way that that's worded. So again, the technical definition of a salt, anything produced from an acid-base double displacement reaction or neutralization reaction. So not too bad. And then finally, what would be our net ionic equation from this? What are our spectators? Because we got to get rid of those. O is not a spectator. B is a spectator. A is a spectator. This is the net ionic equation for every acid-base reaction. That's it. Every acid-base reaction unless it forms a precipitate, which is pretty unusual. Every acid-base reaction has that as its net ionic equation. Hydrogen ions and hydroxide ions produce water. And this is actually, believe it or not, the basis of why the pH system is based on 7. So we'll come back to that here in a little bit. But this fact that this is the net ionic equation for it is related to where that pH comes from. So it is kind of odd that that happens, but that's every acid-base reaction has the exact same thing. Okay, so there's guys that came along later, these other two dudes. You're not going to like them, but these other two dudes came along a little bit later. Do I have it on the next page? Not quite. Okay. I need to do this part. The next two guys came along. Brunstad, yeah. You can just write it's Bronsted. You're American. Bronsted and Lowry, it's two people. But this is called the Bronsted-Lowry in depth because they realized that there were certain things that acted like acids or acted like bases that didn't have the typical hydroxide or hydrogen ions to it. Most of the acids are exactly what you'd think, but it was the bases that got particularly weird. So they had to go a little bit deeper into kind of understanding what it was. And this is this thing that's on this next slide. So what they started to look at was, well, what's really happening at the kind of ionic level when we have something like this dissolved in water? We can think of this as actually being a type of a reaction, because what they found is that it doesn't just ionize. There is at a basic level, actually an acidic level, a very small chemical reaction that occurs in here, which is truly a transfer. What we get in water is some really weird little things. Yeah. This little dude, yeah, that's a weird stuff. This little thing, when it separates into hydrogen ions and chloride ions like that, these little guys don't stick around by themselves. They tend to stick to these guys, so it's kind of a transfer. And it forms a type of a bond that's sort of in between ionic, and it's definitely not covalent, but it's not a full ionic bond either. A little stronger than a typical hydrogen bond. So we get this little weird kind of thing that forms. This little thing has a funky name to it. It's actually what the name of that thing is, called the hydronium ion. How's that for lovely today? And what this thing is, yeah, it's not heavy water. That's made with deuterium. That's just heavier. It's still H2O, not charged. It's just heavy H2O. Anyway, radioactive. That's why you like it. But what they're positing is that hydrogen ions are not really actually free. They're not truly floating around. They're always associated with other water molecules. And this part helped them interpret the other basic side of this particular activity. So we had this was formed. What's the other thing that's left behind? Chlorine ions by themselves. And these, sorry, I didn't mean to change colors, but those chloride ions are sort of freely floating around. The hydronium ions do not spend a bunch of time truly independent. They like to stick with the other, the water molecules is what they tend to form. So we have this weird little complex ion here, thing called hydronium, which is weird. Because this concept helps explain something else that for sure acts like a base that shouldn't act like a base. So I'm going to write, leave yourself a little bit of space because we're going to come back and label this with some other terms here in just a second. So I'm going to leave a little bit of a gap and write something else in here. Now something else weird happens when we put ammonia gas in water. We know for a fact that when we put ammonia gas in water, the result is basic. It is not acting like an acid. We can tell that this one acts like an acid because you can actually test it, you know, put your little dip papers in there, changes color, does all the stuff. When you put this stuff in there, it acts in the opposite way. But there's no hydroxide. So this is that case where this thing we know is acting like a base, but there's no hydroxide present. So Arrhenius's definition isn't sufficient to explain what's happening here. So here's what's happening instead. At some point in time, when we're done, that shows up. If it's acting like a base, a hydroxide is being formed, Not necessarily going into the reaction, it's coming out of the reaction, even though it was not there to begin with. Where's the hydroxide coming from? This little dude's here. Where's this guy going to go? Nope, not going to be by himself. He's going to go over and stick with this guy. This is stuff you've seen. That's why this is ammonia, and that's why that's ammonium. Because when you take ammonia and you dissolve it in water, you form a positive ion as a result of that, and you get hydroxide. Even though there was no base here to begin with, ammonia in water acts like a base. So this is the key of what the Bronsted-Lowry idea was about. How do we include this behavior, which does not fit under what's going on in the Arrhenius, kind of the old school definition. So in order to do this, we have to kind of take a look at the behavior of what's going on here. So Bronsted-Lowry wrote their definition, as opposed to saying it had hydrogen or hydroxide, it wrote the definitions in the sense of being a proton donor or a proton receiver. So I'm going to write this on the board in a second, but a proton donor or a proton receiver. So a proton, what? We haven't been talking about those in a long time. What the hell's a proton? Yeah. Part of the nucleus, right? Part of the atomic mass is the thing that gives it identity, right? The number of protons determines what element it is. So if you have a proton and that's it, what element is it? Hydrogen. It's hydrogen. A proton is a hydrogen ion. That's all it is. Hydrogen with no associated electron to it. And no neutron to it. And if you take a look at hydrogen, hydrogen doesn't have any neutrons, so that makes sense. So when they defined it as being a proton donor or a proton receiver, they're actually taking Arrhenius' definition, kind of like bending it a little bit and making it a little bit more generic. Instead of saying, oh, well, you're just giving hydrogen or hydroxide, you're just giving a hydrogen or you're receiving a hydrogen. Proton donor, proton receiver, which essentially ends up, so let's write that down. So we've got it up here, and then we'll kind of analyze this. So acid is a proton donor, and a base is a proton receiver. And then got to make sure that you realize that a proton is the same thing as saying a hydrogen nucleus. Chemically speaking, they're identical. So now if we take a look at these two questions, we can start to identify them as being acids and bases. What? Mm-hmm. It's ammonia in water, so it's technically ammonium. Yeah, is what it is in there. Mm-hmm. Ammonium hydroxide, ammonium chloride. I actually have ammonium hydroxide over here. When you take it out and smell it, it's got that ammonia Windex kind of smell to it. Super nasty. I hate it. Okay, so hydrogen. How can I say that hydrogen is acting like a proton donor? Yeah, so here it is with its proton, and then here it is afterwards naked. Sorry, proton. Where did it give its proton to? It literally transferred this to that, right? So this is the before, and then after it's donated, we got this stuff after. So this one right here, by the Bronsted-Lowry definition, is considered to be an acid. How is water acting here? Is water acting as a proton donor or a proton receiver? It starts as H2O, eventually becomes H3O, so it is a receiver of protons. So in this particular equation, so again, very different way of thinking about what it is, water is actually a base. It's not a base because it has hydroxide in it. That would have been Arrhenius' definition. We know that water is not a base. When you test the pH of water, it's 7. But it can act like a proton receiver. And if you have something that really wants to give away hydrogen strong enough, it can act like a base. So we've got an acid and a base. We also want to name what these things are, the species that are left after the gift has been given or received, so to speak. So here's what's kind of weird about these. This thing, after given away its hydrogen, is no longer considered to be an acid. This side of the reaction, this thing is called, I'm gonna put the abbreviation up here, and then I'll give you what the CB stands for. The C is called the conjugate base. It's 2 words. So the acid becomes the conjugate base. Just think about it in like Spanish class. When you conjugate a verb, there's kind of like the original version of it, and then there's the after version of it, right? After you've conjugated for your forms. That's kind of what they're talking about here. There's your initial version, and then here's after it's kind of gone through the ringer a little bit. You get your conjugate base. So what's the water going to be? If this is the base, conjugate acid. Again, the same word, conjugate. Why does this matter? Chemical reactions, especially acid-base reactions, oftentimes don't just go one way. They're reversible reactions. And so if you look at the reverse reaction, this thing, does it act like a proton donor or a proton receiver? If you're going from right to left, it's acting like a proton donor. So if you think about the reverse reaction, this thing is going to act like an acid. It gives a hydrogen away and then becomes the base over here. So that's why they kind of swap sides in terms of the acid becomes the base and the base becomes the acid, because you're talking about the forward reaction or you're talking about the reversed reaction. Which way are you sort of facing? Let's take a look at the bottom one. Okay, which one's acting like the proton donor? That would be our acid. Yeah, from here to here, is that giving away or receiving? That's receiving. And from here to here, is it giving away or receiving? This one's giving away. So this has got to be our acid in this case. And that would mean conjugate base. So it's kind of the before and after. They swap sides. And I'll do a completely spare one here in a second. Ammonia starts as NH3, becomes NH4, so it's receiving. And that means this is acting like a base. And that's how we've got that definition of the acid-base reaction to it. And that means that NH4 is actually a conjugate acid. Again, this particular idea, this Bronsted-Lowry definition, explains a much wider variety of acid-base behavior from things that are not typically what we would call acids and bases. Arrhenius' definition works most of the time. In the sense that you plop it down there, all right, now I understand. There's a hydrogen, there's a hydroxide, I know which one's the acid, which one's the base. But there are cases like this where you don't have the typical acid or base, and yet it still acts like it. What's weird about this one is look at the behavior of water. Water sometimes acts like a base, sometimes acts like an acid. It goes both ways. It's happy to have either one. It'll give one, receive one, depends on who it's with. This is not a vocab word that you need to know, but there are a very few terms, very few things on our planet that actually behave like this, where they can act like either an acid or a base depending on who they're with. Either give or receive depending on who they're around. Those are substances that are called amphoteric. And it just happens to be pretty rare in the universe. Our planet just happens to be covered with one. One of the other reasons why water makes such a great solvent, because it's amphoteric. It has a lot of variety in terms of what it can do. It's so balanced kind of within that molecule, but yet polar within that molecule that can do. It's a cool molecule. And again, we take it for granted just because we're covered in it and made of it and everything else, but it's pretty awesome stuff. I'm not testing you on this word, so if you're a word nerd, enjoy that. I'm not putting this one on the test, I don't think I put that on the test. But yeah, water's weird. It can act like an acid if it's around a base. It can act like a base if it's around an acid. Kind of like some of you act like a good kid when you're around the bad kids. When you're around the really good kids, then you act like the bad kid. Just depends on who you're around. Clyde, I'm talking to you. So he's like, Clyde's like, I'm not a bad kid. I'm amphoteric. And how we doing? Yeah, you're not even awake yet. You have no idea what I just said. Shrugs. Okay, this is one of those skills I'm going to ask you to do on the test, so take a second and practice it. This is one of those things I'm going to ask you to do about applying the Bronsted-Lowry theory for both of these two. This is supposed to be one of those kind of double arrows that my computer does not do very well, so that's what that's doing. See if you can just do a quick label. I don't care if you copy it in your book off on the margin or something along those lines. I want you to identify acid base, conjugate acid, conjugate base. A, B, C, A, C, B. They're not always in that order. Again, copy me if you wish, or just kind of look at it, eyeball, whatever your preference is. I don't know if I marked you here. Quinn, let me Make sure I actually got you here. So your mom, oh, yeah, you can get the phone call. Hey, Quinn, you doing this or not? Mm-hmm. Quinn made it, okay. Roberto did not make it today. Zev did not make it today. Melanie did not make it today, okay. Update that, sorry. Again, identify the pairs left and right. Which one's a donor, which one's a receiver? The top one's showing water's little weird nature. Bottom one doesn't have anything obvious in it at all. That's why I put that one in there. Where it does not, this is a true example of Bronsted Lowry where there's not the obvious things in that one in any way. When I'm attacking these, I try to find the pairs. Following the anion a lot of times is a little easier. If you can't see the two pairs, it can be a little bit awkward. I will try to, whenever I do this for you, give you ones that try to make it sort of obvious, kind of who's with who. I think I just accidentally labeled them in the correct colors too. Okay. It doesn't really matter. Water, H2O to H3O, is it acting like a proton donor, which makes it an acid, or proton receiver, which makes it a base? It's a receiver. So this is a base, makes that side the conjugate acid. Verify it to make sure you're right. H2CO3 is carbonic acid. That's the name of that one. Is it truly acting like an acid here? Yeah, it's giving one away. Notice how it only gives one away? That's pretty normal for acids. So this is the acid, and this is the conjugate base. Down below, HOCl. Is it acting like a donor or receiver? This one's acting like a donor. So does that make it an acid or a base? That's the acid. This would be the conjugate base. That thing right there goes from 2 hydrogens to 3 hydrogens. So that one's acting like a receiver. So this must be the base. This is the conjugate base. Sorry, conjugate acid. Kind of a weird little skill, but I will ask you to do this with acids and bases, including ones that are kind of non-traditional, to be able to identify what they are. This one, by the way, is an acid that you should be able to name, although it's a hard one. This is how you're used to seeing it written, as opposed to HOCl. Okay, which ion is ClO? Nope. Chlorate, chlorite, hypochlorite. Yeah, hypochlorous. It's an ite. Hypochlorous acid is the name of that one. H2CO3 is carbonic acid, hydrogen carbonate, so it becomes carbonic acid, or carbonic is how it's pronounced. This one's a weird one to write. By the way they wrote it like this is because the hydrogen actually sticks to the oxygen, not to the chlorine. That's why it's written in that order, but I'm not going to make you figure that one out at all. Weird. All right. So I'm sure you've seen something like this before, where you have, that's water, very exciting. I put some stuff in there. There's some really cool things that are called indicators, in case you aren't familiar with these. I think you probably are. You're going to use a different indicator tomorrow, which looks a lot less interesting, but it has a cooler response to it. This indicator is called universal indicator. It's not actually one thing. It's actually a bunch of different indicators on here. What's kind of cool about indicators is that they have a way of changing color depending on whether in the presence of hydrogen or hydroxides. It literally, the amount of other things that are in there change the reaction to them. So this is hydrochloric acid. So if I put that in there, that doesn't look, hopefully there's enough. Doesn't look super exciting until you kind of get it to mix in there. I need to get some more of it. That's this one. So as you start to do that sort of thing, it actually changes what its color is. Magical. Let's sit there for a second. So this was hydrochloric acid. This was water. The green stuff is just this universal indicator. And so green tells you what kind of pH. the color green. This was water to begin with. Neutral is the word you're looking for. Green means neutral. And this is not neutral anymore. This is a long way from neutral. This is hydrochloric acid. So a red end of the spectrum is considered to be acidic. So what's nice about this is that indicators are sort of like, they're not really catalysts. They are reactants. They do actually physically change a bit. But what's nice about this is it is a physical reaction that is reversible. So if I have enough of this in here, I can start to get it to go the other way. Hold on, let me give it enough to work. I need some more of that. Magic. All right. So what's the pH now? About neutral, right? And then there's more sodium hydroxide. How did I get that perfect like that? I couldn't have done that if I tried. All right, so if I keep going with it, so you can see what the other end of the spectrum is. There we go. This isn't 14. This is probably like 9 or 10. But if I put... No, well, there you go. We get up into that range. There's a nice little violet kind of color. That's more like 12 is what that is. So in terms of the colors to it, there we go. We'll let that kind of do its thing. It's definitely a reversible. I can kind of go back and forth with it. That's the other one. Nothing like unlabeled droppers. Make sure I have the right one. All right. So I don't want to make hydrofluoric acid. No, I don't want to do that. All right. So I want to get this close. Yeah, it's like magic. There we go. And then, got to get some more. Once again, green. And then I can kind of get it to do the tourmaline thing that it does. There you go. Where it's kind of like one color at the top, one color at the bottom. Yeah? Is it not? A little bit. Hold on. So this tells you something about how these reactions occur. They're a little bit slow. They're not instantaneous like you always think they are. And as soon as I let them all come together, then I can get it to kind of change the rest of the way. So the reason why it does, that's more like a 2 in terms of acid, that particular dark red color. Some hydroxide, there we go. I need to move these by their friends. So, what was that? I can get it to do the other way on top. Come here, sodium hydroxide. It's trying. So you can kind of do the same thing where you can get that combination on top, where you can get that, what was that? You can only do that a certain number of times. I can do this forever until the beaker gets full, and then I can dump half of it out and keep going. And again, once you get it in there, you can see the color in the bottom is starting to shift as some of those hydroxides are sort of drifting downwards. There's a bunch of different colors in here as you can kind of literally see the hydrogens and the hydroxides sort of coming into contact with one another. Depends on so many different things in terms of how exciting you want to make it. It can be, they don't have to be. For example, I can do acid-base reactions with stuff and not make it quite so. No. Am I wearing safety gear? I don't really want to, but hold on, if I can get it to go. Not entirely. If I can get it to go. There's green, so that's pretty neutral. And, oh, see how it wants to turn yellow or turn red? It kind of starts, and then it goes back. Now we're at yellow, and now it'll pop over the top. Oh, it'll stay orange. Nope. Need to drink some water, man. Not okay. And if you go to the bathroom like that, man, you seriously have some trouble. So that's not okay. Definitely not all right. So infinitely reactable. Infinitely reversible. All I'm doing here is I'm adding extra hydrogens, shifting it one way, adding extra hydroxides, shifting it the other way, letting it kind of go back and forth so that it can kind of do both of them as we kind of go, as we kind of reverse it. So we're on the acid side right now. I want it to go back to neutral. Will that one work? I have enough of it in there, if I had any of it in there. The concept of strong and acid, strong and weak, though, is very different. What's in here, I've done this a few times, and I'm lucky today, apparently. It'll probably shift to yellow. No, it did. As I was saying, it's going to probably shift to yellow. Hold on. Okay, well, I want to go towards green. I'm going to give it one drop. Let's see what it'll do. And think. Okay, it'll probably shift to yellow. Get an actual drop there. Okay. Okay, it'll probably shift back to yellow. Why is it doing that? Hold on, let's get one more actual full drop in here. Not with this. So what do I have more of in here? Think about limiting reactants, excess reactants. What do I have more of in here? A little bit more hydrogen, right? A little bit more. But then if we let it sit there for a sec, it may stay now. Those extra hydroxides that are running around there sometimes can start to grab the extra hydrogens out of there just a little bit. And as I get closer and closer to true neutral, that color shift is taking longer to happen, right? Because they're getting much more balanced. At some point in time, you'll put it in there where it'll turn green, it'll stay green. And that, nope, nope. Stubbornest reaction ever. There you go. What is it, lawful evil? Lawful neutral. Nope. Dang it. Nope, nope. Yeah, we're literally playing right around that neutral point. There we go. One more drop in there. I know it's like the most boring demo ever. There you go. Slightly on the blue side of green, so maybe it'll stay. Maybe. Let it sit there for a sec. Hashtag oddly satisfying. What did you guys do in class today? We watched it turn colors. So what's kind of cool about this is you can actually see that rate of reaction. You can see the fact that hydrogen's pretty stubborn, or so to say, water is pretty stubborn. It doesn't necessarily want to give up those hydrogen ions. It will, or absorb those hydrogen or hydroxide ions. So it's sort of slowly but surely absorbing the hydroxides, releasing some of those hydrogen ions that's in there. Just barely green. So anyway, it starts to change color as we're doing that. This concept like this idea of shifting things back and forth, I'm using a strong acid and a strong base. The term strong and strong does not mean concentrated, because everything I have in here is actually the exact same concentration. These are all 1.0 molar, 1 mole per liter, 1 mole per liter of hydrogen chloride, 1 mole per liter of sodium hydroxide. This is ammonium hydroxide. I don't tend to use it as much because I really, really hate the smell of ammonia. But ammonium hydroxide should do the same thing. This one should go towards the blue side, and this one will probably now stay here because I've kind of nudged it over. We'll see if it does. But ammonium hydroxide is still one of these things where it's considered to be kind of a strong acid, strong base kind of situation where it's really available. It's going to stay green now. It's going to be really available to kind of do what it wants to do. However, we have a weak acid up here. Weak acid is vinegar. Notice how we don't put hydrochloric acid on our salads. We could, it would not be delicious. When we put things like hydrochloric acid, those hydrogen ions are pretty nasty. And if we start to do these guys in here, where I put a drop or two of vinegar in here, now this is the same concentration. This is still 1.0 molar. Okay, as it starts to change, every time I put a drop of this stuff in there, I know it sounds kind of weird to put it. Yeah, acetic acid, CH3COO. It shifts, but a lot less. Like when I put 1 drop of hydrochloric acid in there, it kind of goes to that red and then shifted back. This stuff is kind of like barely goes to orange and shifts back. See if I can get another actual real size drop on there. That's not a drop. That's an air bubble. That's an air bubble. There we go. So when we're doing this particular way, as I'm adding this kind of stuff, it's going to take a lot more of the same strength stuff to get this to finally change. My wrist is going to get tired after a while. There we go. Okay. And it's not there. It's yellow. It's going to go back to, or it's orange, going to go back to yellow. So even though I'm adding a substantial quantity of this stuff is acting a little bit different than the hydrochloric acid. Put 1 drop of hydrochloric acid in here. The stuff will start to go towards that red and kind of stay on the red side. This has definitely got a little bit of a different behavior, even though technically it's the same concentration. So concentration and strong and weak are not the same idea. And that's what I'm going to put up here on the board next. Again, this is good on salad. This is the good kind of sour. Tangy, right? This kind, this is eat your face. This kind only gently eats your face. Yeah. If you ever have vinegar on something and you've got like a cold sore, like a canker sore in your mouth, still eats your face. But doesn't eat your face like hydrochloric acid eats your face. So there's a little bit of a different sort of style. There's a lot of things that we put in our foods that have the word acid in them that are weak acids because you don't want to eat strong acids. They're tangy, but too tangy. Okay. So, too tangy. Okay. Okay, so strong acids. I'm writing this now as sort of an equilibrium reaction to show that it's kind of battling with the waters. Is it going to give away its hydrogens? Is it going to take it? What's it going to do? And what's different about strong acids versus weak acids, and I'll do this. The one I'm using right now is vinegar, HCH3COO, also known as acetic acid or hydrogen acetate, plus H2O. Wow, 2O, there we go. Okay, what's our conjugate acid going to be? Conjugate acid. Conjugate's got to be on the right side. Name is? I want to know what my conjugate acid is. So this is what remains after this has given away its proton. Oh, no, sorry, I said it backwards. After it's received its proton. So we would have this guy. Once it's received its proton, we get this thing, H3O, which name is called hydronium. Conjugate base is what's left behind after this has given it up. That's acetate. Chiku. So these both look exactly, pretty much identical in terms of their view. They act with water, they make hydronium and an anion. Exciting. The way that one's strong and one weak is we know this based on certain behaviors, like how it fights changing pH. But the way it does it is explained in here, in these two little arrows. The key idea is that with a strong acid, this direction is like massive in terms of what it does. It's very little of the backwards. Very much so. Pretty close to 100%. It will fight back just a tiny bit, but pretty much it's going to send all the way over to the right. When you put hydrochloric acid in water, it's pretty much all of those hydrogen ions are released from the chlorides and are held in the form of hydronium ions. Vinegar, it's a different case. Yeah, it's more like, you know, this. Yeah. Kind of favors them both, yeah. There's definitely some of these are produced, but not as many as something like this would be. Kind of favors both. In fact, this as a weak acid does indeed favor the reactants just a little bit. So when we put vinegar on our, you know, salad dressing or whatever we want to, we get the sour flavor to it, but in a very small percentage for the same concentration. So a couple of things to keep in mind. Strong is a chemical behavior, concentrated is a physical behavior. Strong is related to reactivity. How much does it dissociate? Concentrated is physically how much water is it combined with. So you can have a concentrated and dilute solution of either a strong or a weak acid. Oh my God, okay, so let's try this again. When we talk about 1.0 molar hydrochloric acid is a strong acid, and 1.0 is fairly concentrated. Yep. There's acetic acid right there. Okay. Acetic acid is a weak acid. But this is 1.0 molar concentration. So it's concentrated, but weak. There is, if we had the same exact quantity side by side, these are both 1 molar, there's way more hydrogens available in this one, it's a strong acid, than in this one, it's a weak acid. That kind of make sense? You can have a very dilute strong acid, like 0.01 of this, that's actually more dangerous than 0.5 of this, because of the actual amount of hydrogens that are available. I'm not going to make you do that math. You're welcome. But I need you to have that concept of what that is. What? You're going to actually tell me that in lab tomorrow. That's going to be your job. It's 5%, but you got to tell me what the actual concentration is. So strong and concentrated are not the same. You can have a concentrated strong acid or a concentrated weak acid, or a dilute strong acid or a dilute weak acid. They're completely separate ideas. Again, one's related to how many hydrogens does it release. One is related to how much water is it stirred into. Yeah? Okay. So, by the way, this thing, which comes along a little bit, I'm also not going to make you do much math on this at all either, but I want to mention what this is, since we're talking about hydrogen availability. Okay, so I'm specifically using square brackets here. I'm not using parentheses. They're not parentheses, they're the brackets. Yes? So brackets like this is the physical way that concentration molarity is abbreviated. So when you see something in square brackets, this is talking about the molarity of hydrogen ions. That's kind of how you would read that. Again, square brackets means molarity. So what this is, you've heard of that particular value, pH. By the way, pH is always lower, H is always upper. P is always lower. You cannot start a sentence with pH. It has to do with like proportion. So it's more of a mathematical function than anything else. The way I think it's a logarithm is what it is. But I think of it as related to the proportion of hydrogen. So here's the function. Oh, crap. Yeah, not natural. So it's base 10, which is really nice. So in water, pure water, water will kind of fall apart a little bit. So if you're talking about regular pure water, there's a very, very, very small amount of hydrogen that's just hanging out. By the way, this is a 1 with 6 zeros and another 1. That's not a lot of hydrogen available in pure water. If you put this into a calculator, here's what's kind of nice of it. And you take a log function of this. I don't know how much algebra you've had, because I used to hate log functions, but just one of those things for me. Doing the log rules and all that stuff's kind of hard. We don't have to worry about that. Here's what's nice about log functions. If you have a log function of this number, I take the negative log of that. The log function outputs the exponent. If I take the log of this number, it's going to give me the exponent back. So if I take the negative log of it, it makes that value positive. So what that means is that when I take the negative log of that natural state of water and I function this through a calculator, the negative log of that concentration is 7. Yep. Yep. If I have in an acid, I might have something like this, where the hydrogen ion concentration is something like 1 times 10 to the minus 3. Okay, I'll remind you, this is a bigger number than this one. I know, but looking at it in scientific notation is weird. 2, 3, 4, 5, 6, 7. 1, 2, 3. Right? This is much more concentrated hydrogen. So if I put the negative log of that, what's the pH of this thing? 3. Because it just literally takes that out. It just gives you the exponent. Now, if we start putting other numbers in here, like 5 times 10 to the minus 3 or 2.75 times 10 to the minus 3, it'll change the pHs a little bit, and you get like in between 2 and 3, you can get a pH at 2.5 or a pH at 2.7. You can get in between kind of zones. Again, I'm not going to make you do the math on this. I want you to understand that it's related just to that exponent, how concentrated it is. When you have a basic solution, how much hydrogen's in a basic solution? Approaching none. Basic solutions have hydroxides, not hydrogens. So these things have really small versions of this, like 1 times 10 to the minus 10th. And the pH of that is 10. So what sometimes is more valuable for basic solutions would be to know the other side of it. And I'm just introducing this concept as well. I know that these two go together for a bunch of reasons that you don't care about right now. If I have a concentration of that for hydrogen ions, I will have this for hydroxide ions. It always adds up to 14. But we can't call this is pH. It's the pH of the hydrogen ions. Yep. This thing right here is called a POH. And if I want to give the concentration of the hydroxide ions, if I'm working in basic solutions, it's kind of the same idea. POH, OH. So we can talk about basic solutions just like we talk about hydrogen solutions. They're complementary. So the higher the pH, the lower the POH, and vice versa. So they kind of follow the opposite paths. You're just used to pH scale being from 1 to 14. The POH scale is also from 1 to 14, but maybe I should say it's from 14 to 1. It goes the opposite direction. What? Why do you typically learn about it? We tend to do a lot more acidic stuff than we do basic stuff, but there's a whole field of chemistry and bases where this would be much more important for it. Kind of makes sense? So certain types of redox reactions especially are better in basic solutions. Once you know one, you know the other one. So tomorrow, you guys are going to be doing a lab. And I want to do a quick demo of this. Tomorrow, I don't know if you guys have heard the news, the WASC committee is here. The accreditation committee is back. This is a totally, this is a totally normal routine visit. They always come every 3 years and just kind of peek in and go, how's everything going? So this is actually a very routine visit. This is not, this is definitely not worthy. That was the last couple of years that we were having those sorts of issues. This is not that. This is just them coming in for kind of their checkup or whatever it is. So there's a decent chance that during first period tomorrow, I won't be here. So I want to make sure that I have a little bit of physical view prep for what we're going to do tomorrow. You guys are going to be doing an acid-base reaction. Okay. Yeah, this is a graduated cylinder. It's actually, it's a high school cylinder. You guys are going to be telling me at the end of tomorrow, this is acetic acid solution. I know what this is. You're going to tell me what the concentration of vinegar is, what the actual molarity is. I know it's 5%. Don't Google it. I'm going to have you determine it. So I would like you to think of this as a fairly straightforward acid-base reaction. So fairly straightforward acid-base reaction. What are we going to get? Okay. Oops, I wrote that wrong. So by the time we do our products, we should get water and a salt. In this case, the salt is sodium acetate. The stuff that's used to make malt vinegar chips, malt vinegary, it's sodium acetate. You can look on the ingredients, but they use that vinegar salt. Like salt and vinegar. It is. That's why they call it that, because it's just salt and vinegar. If you put vinegar on chips, they just get soggy. Right? But it's the acetate ion that gives it that malty kind of vinegary flavor that you're used to. So, oh my God, it just melts the chips. So here's how this is going to work tomorrow. The basic logic on this. go. Sorry, guys. Your end goal is to figure that out. You're going to know what this is. Let's say for easy math, on paper, how could you figure this out?
Have a certain amount of NaOH, liters of it. You can find out how much there are.
Yeah. So here's what you're going to end up having is a few known pieces. This one, I'm putting this up super easy right now. If I have 50 mils of vinegar and 50 mils of sodium hydroxide, neutralize it. Then I could figure out how many moles were in here, and I would know how many moles were in here because they're in a 1-to-1 ratio. And then I can work backwards to figure out what the molarity is. If I know this information right here, I can calculate how many moles are present because this is in a 1-to-1 ratio. So if I know that however many moles this is, same moles are present. I know what the volume is. I can work backwards to figure out what molarity is. Okay, what if it's not 50? Random number. Crap. What would I do? Figure out how many moles, right? Do the math. I know that this is in a 1-to-1 ratio. They're not always 1-to-1 because I could use sulfuric acid, which is 2-to-1. I'm trying to make your life tomorrow easier, not harder. So this would be in a 1-to-1 ratio. So however many moles were in here would have to be the moles here. And then we can use this information to figure out how many milliliters were there, right? So how we're going to do that for real, it's really hard to know when it's neutralized. A clear solution and a clear solution makes another clear solution. Boring. So what I have up here, this thing is called a graduated cylinder. Graduated cylinder with a volume-y thing on the bottom, and a nozzle is called a burette, B-U-R-E-T. And this thing is a graduated cylinder that I can tap out the bottom of it as opposed to a regular graduated cylinder we pour from the top. So this thing in here is full, kind of, with sodium hydroxide. It's to this level. This is the 0 point, but there's lines on here. Could I figure out what this volume is right here? Yeah, just read it. It'll take you a second to figure out how to read these things. They are definitely a bit different than other graduated cylinders that you've read. So you'll have to look closely at the lines that are printed on there. Figure out, is it going up or down, and try to figure out what the volume is. Down in here, I have some vinegar, which is very exciting. And then I have the nozzly bit. So here's the tricky part for you guys, is that we need to add this in such a way that I know exactly how much of this got used. So I need to record that value. I don't care what it is to start. I just need to know what it was to start. It's kind of like zeroing the scale. And then I'm going to add it drip by drip until this changes. You guys are going to use a different indicator tomorrow. There's indicators already in there. This stuff has a horrible name. It's called phenolphthalein. There's lots of P's and H's and TH's in there. Phenolphthalein, P-H-E-N-O-L, P-H-T-H-A-L-E-I-N. Don't spell it. Phenolphthalein is this stuff. And phenolphthalein has some kind of cool stuff that it does. Let's see. I'm going to swirl it this way. Okay, I have to get this twisted around here. Okay, hold on. Awkward. By the way, this thing is called a burette clamp. You can just squeeze this to adjust up and down if you need to. So don't get it so low that you're doing the, tink, tink, tink as you're trying to stir. But you don't want it so high that it's going to splash out all over the place. And I'm doing this quick and dirty because I know we have, 10 minutes left, if that? A little under 7, 5, whatever. So kind of down low like that. This, again, is sodium hydroxide. This down here is vinegar plus a little bit of phenolphthalein. What color is phenolphthalein in an acidic solution? Colorless, clear, right? So you're going to add this drop by drop. I don't want to add it too fast because I don't want to overshoot and have it go all the way to one side. I want to know exactly what it is. There's a cool thing about phenolphthalein where it'll change color right around the neutral point, very close, within a drop or two. And for our level of sig figs, it's enough to say, okay, that's neutral when it changes. So here's the tricky part that I'm going to make. I won't be here tomorrow to make fun of you guys. I may not be here. So figure out which hand you swirl with. I'm a right-handed swirler. And you'll know because you're going to go like this on the tabletop. You're going to try to do it with your other hand, and it's going to be like trying to brush your teeth with the wrong hand. I could actually do it with both, but I'm much better with my right hand in terms of swirling. Okay, so figure out which hand you are a swirler. Yeah, so far so good? Okay. Your left hand then typically is going to have to be the nozzle hand. Stop and listen because I'm giving directions I cannot give tomorrow, and this is tricky. So please pay attention with your utmost focus, which for some of you, my cat could do better. Okay, so take a look at the way I'm holding this. So everybody wants to grab it this way. That's the hand you're swirling with. This is the hand I have to actually use the burette with because I'm going to be swirling with this hand. And it's not a one-handed deal. And this is not a two-person deal. You'll look like a moron. You go to college and one person's swirling and the other person's doing the nozzle. I will not have people leaving my chem lab thinking you're a moron. About their swirling anyway. So with this, make sure that you're swirling with this hand. When you grab the burette nozzle, you may not grab it from the outside. These things can pull out. And if you pull this out, now you have concentrated sodium hydroxide that's going to dump out the bottom of this thing. That's bad. So you want to make sure that it's such a way that as you are using this, you're not pulling it out, you're sort of pulling it in. So you can kind of see I'm grabbing with my hand sort of around the tube. And then you literally just add it slowly, drip by drip. Sorry, give me like 2 seconds, guys. You can turn it on so it just barely starts to go drip, 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 like that. And you can kind of see where the color change starts to get to be. What colors are going to turn? Yeah, and I'm going to do this real quick so you can see what it is when you're at the end point. Let it go. It's really stubborn as you get close to the end. Just like that one likes to change color back, so does this one. Yeah, this one does pink to clear really quick. So you have to kind of get to that spot where it goes, pink and then stays. That's too dark. That's too dark. I want it to be like pink and just barely pink, but staying pink. That's kind of where you're going tomorrow. There you go. I'll try to be here, but I don't know if I will be. I want orange. Let's see. I need some vinegar in there. What is it?
Chapter 4.
Oh, okay. I'll take it.
Just kidding. It's chapter 3.
Is it chapter 3?
Yeah.
Chapter 3. Thank you. Yeah, fabulous. Yeah, a couple of you guys I know are getting there. That'll work. See, guys, that's what I want. Not enough time in the class when I'm not going to be here tomorrow. Inconvenient. Well, I want it to be. Well, it's really fun to watch it start to go. And then it'll just disappear. I mean, that's just wild that it does that. Trying to get like one drop is always the trick. Oh, come on. One drop. One. Just one. Oh, that's too far. That's too much. Yeah, that's always. Oh, magic. That's kind of how it is on this lab. You want it just enough. It's all right. What's up?
Can I come in after school to finish my test?
Absolutely. Yeah, no, I'll be here. I'll be here late tonight and Wednesday. So,
Thank you.
Yeah, absolutely. There we go. That looks good. Will you?
Yes.
Fabulous. You're close, aren't you, Jacob? Yeah. Kinda. Kinda, but not so much, but kinda, but sort of, but kinda.
A little bit.
All right, I want to do.
Oh, no.
Literally, it's that close. I need like a half a drop. Can I get a half a drop? Nope. Well, crap. Now that's going to be way over. Let's get it back here. I want to get one balance so I can keep it for just a little bit. I mean, that's like way too dark where it's almost like red. 2. Isn't that amazing how pink it is? Oh, look at that. That's a perfect pink. See how light that is? You can still see that it's pink. That's about as good as it would. That's lucky is what that is.
That's what we want?
You're going to have probably one more tiny drop, and it'll hopefully be just a very light. Can I get a half a drop? kind of in there. That if you get that color without it being the red, that's actually pretty good. Like I said, it is so twitchy that literally that is 1 drop to a half of a drop difference. But you can see how I mean the tiny amounts that I'm adding to get that to work. So I'll leave that there as a demo for later. Okay, I need you to be green. What?
I wasn't here for the stoichiometry challenge lab.
Lame.
Oh.
Were you here for any of it?
For like the last day, but they had already done all theirs, so I really didn't do anything.
Shameful.
So.
Because you were here for the last part. What you should do is turn in and then put that note like, hey, absent for whatever, and I can excuse you from it. It's fine. Yep. Yep. No worries. Vinegar, sodium hydroxide. Jesus is not here right now.
Yeah, he is. He's right here. Get it?
Is it you?
Yeah.
You look different than I expected.
Hey, Miss Bethel, I wanted to ask something about the Europe trip before I moved to that. I remember when the Europe trip was being handled by the language department. That they weren't taking seniors on the trip.
Okay.
Is that still a thing?
So I will agree to take seniors under some kind of limited circumstances because you guys haven't had a chance to really go. But the big thing that you need to understand is that it's not a party trip. It's not a drinking trip.
Yeah.
It's not the senior trip. If you can handle that code of conduct, then I'm okay with you going.
Yeah, of course, yeah.
But does that make sense?
Yeah.
But that's the thing is that some people were treating it like, oh yeah, it's the big party trip. And it is definitely not that. So if I can talk with you and talk with a parent and you guys can agree that, no, I'm not going to go drink on this. It's not going to be that sort of craziness.
I mean, I would like,
so
to be perfectly honest, I would do it. But
well,
only like when it's acceptable.
No, exactly. When we're in France, you get a glass of wine with dinner. When we're in Germany, you get a glass of beer with dinner. That's the accepted part of that trip. Yeah. But it's not
like you go get
you're not going to discos, you're not doing some of the crazy stuff that a lot of times get associated with senior trip. Does that make sense? So that's my concern. So if you think you can abide by that behavior, then yeah, then we're good.
Yeah. I was just wondering because
yep.
I remember seniors were like totally banned.
And the reason why is because they weren't very good at respecting that. And so we'll try it. If it works, great. If it doesn't work, I'll never do it again. Make sense? Yeah. What do you want? This is for your class, so you'll get to watch more anyway. Yes. Sorry, what did you want to do?
I don't know. I left my book at.
Oh, your notebook?
Yeah.
Just do a separate paper and tape it in. Yeah. No, super easy. Just do it on regular paper.
I don't want it.
It's not a big deal. I promise.
Well, I forgot my whole bag.
You're a disaster is what you're saying.
Yeah.
You're just a mess. You're like, oh man, what have I done? Okay, so that I need a little splash of vinegar. Vinegar. This is your lab that you guys are going to do tomorrow. Okay, and then I need a little bit of the phenolphthalein. Okay, I'm going to make sure that you know how to spell this. If you don't spell this correctly on the test, you're fired. Isn't that a great word? PHTH is how it's usually abbreviated, which I think is pretty logical. Okay.
Does it not matter?
For that stuff, no. That's an indicator. It's just a color changer, kind of like this one. It's just a different color. No, they're the opposite side of it. Limited's the one that runs out.
Okay. Yeah, but like for solving it, is it the same?
Yeah, same process for solving it, just a different choice. Yeah, so yes and no. How's that? Okay. Am I recording still? Hey, look at that. You're on there. Hi. Guess you forgot to hit stop. There we go. Second period. Hi, Nate. There's Nate. There's Tyler. Yeah, bye. Sorry, I forgot to hit stop. Wow, that's really long. Yay. Yeah, too much time.